Hello everyone. Today is day 4 of this challenge where we are solving 30 machine learning problems, or I say we are doing 30 deep learning projects in 30 days. So let's get started. The title for today's problem is to compare activation functions, which is rectified linear unit, sigmoid, and 10H on fashion MNIST data set. So I will go to the chat GPT. We will follow the same steps. Ask chat GPT with the questions like give me I mean today I mean give me the code, explain this and that. So yes, let's start. I will use the same window that I had used for the last three problems. So let's start with saying, hey, it is day 4 and here is the problem. So it says that comparing activation functions is like understanding how they influence a neural network, ability to learn and generalize. Today, we will explore fashion MNIST dataset and compare the effect of different activation functions, which is, we will go through the rectified linear unit, sigmoid, and 10H on the model's performance. Problem outline. We will train multiple neural network models on fashion MNIST dataset. We will vary the activation functions used in the hidden layers. These are the activation functions, and then we will observe how each function affects training speed, accuracy, and generalization. So let's see how the problem is looking like. Mm, mm. We define this function, and then we'll go ahead and use this activation function for all the all the for performing all the steps, and then we will generalize. Okay, let's start. So let's understand about a little bit about these activation functions. Activation functions help introduce non-linearity into a neural network, allowing it to learn complex mapping from input to outputs. Let's briefly summarize the three types. So we saw that activation functions, they, in simple language, what I have understood is we have we have neurons in layers, and then decide which neuron to turn on and turn off for predicting with more accuracy. We have activation functions. So first one is rectified linear unit. The formula is this, which is fx mx max of 0 and x. It is fast to compute and solves. It is fast to compute and solves the vanishing gradient problem, common in deeper network. Okay. uh, I do not have much understanding even now, but let's follow through it. And then we have a sigmoid activation function, which is 1 plus exponential of minus x. Outputs value between 0 to 1. It is prone to vanishing gradient, especially in deeper network. Okay. Then 10H. The 10H, the formula is exponential of x minus exponential of minus x divided by exponential of x plus exponential of minus x. Outputs values between minus 1 and 1. It is similar to sigmoid but tends to be centered around. So the output values is between minus 1 and 1. It is similar to sigmoid but centered around 0, which can help with training. Um, okay. I don't want, so let's go further understanding these three activation functions. I don't want to go further. I don't want to go deep in maths and formula. Can you explain the three activation functions in simple words with an example? So let's understand in simple words, right? So we are learning it. We do not, I don't want to bore you guys and bore myself at this time. Also, I don't want to get overwhelmed with maths and everything at this point. Maybe once we understand these concepts, and then we will go, I'll go and pick up these topics one by one and go deep and understand the formula and maths everything. So yeah, it has generated the response. So let's go through it. It says that the rectified linear unit, with what is it? It stands for rectified linear unit. Think of it as a function that passes positive values as they are and stops negative values and turning into them zero. When the positive values means that it is going to pass the value, and the value is negative, it is going to stop it by turning them zero. Simple example is, imagine you are listening to a music player. Okay, the volume knob can go from -10 to +10, where negative values mean turning the volume down, even making it mute, and positive values mean that we are turning it up. However, rectified linear unit does not care about the negative values. It just ignores all the negative values and keep positive values as they are. Okay. If the volume knob is at +7, the rectified unit will out let it let will let 7 through. But if the value is minus, it will not set. It will just stop it, as in it will just turn it to zero. That is mute it. So any value less than zero will be muted. Any value more than zero will be like that, and the rectified linear unit function pass it through. In neural networks, rectified linear unit acts as a gate. If the input is positive, rectified linear unit lets it pass. If it is negative, it blocks it and turn it into zero. This helps the network learn quickly without it only needs to deal with the positive. Okay, that is why it is fast. Why? Because it is dealing with the positive signals only or zero, and all the rest of the signals less than zero, it blocks them. Summary of rectified linear unit. The summary is that the positive inputs, it uh, passes through, and the negative input, it blocks them. Analogy is that it is like a music volume knob that ignores negative adjustments and lets positive adjustment go through. This was better. So we understand that it passes through the positive values, it blocks the negative values by turning them zero. That is why it is fast. Um, Now sigmoid. The sigmoid function squashes input values into a range between 0 and 1. Okay. It is useful when you want to decide something in a probabilistic way, for example. So it squashes the input values between the range 0 to 1. We can think of it in a probabilistic way. For example, is this true or not? Because 0 and 1 represents extreme. Okay. Example would be a light dimmer. Imagine a light dimmer in a room. You know a knob to control the brightness of the light, but the light can only be between 0 and full. 0 means off, full means full bright, 1. If you turn the knob slightly, you get a value close to 0. If you turn it more, you will get a value close to 1. If the knob is in the middle, we get a partial value like 0.1. In neural network, sigmoid takes the input, squeezes it between 0 and 1. It is often used when the output layer for when the out, when the output layer is a binary classification, where you need to determine if something is of one category or another. Yes, remember we use softmax rectified linear unit, sorry, softmax activation function, which was also giving probability of whatever neurons we pass, and the sum of those probability is going to be 1. Here it also, this sigmoid gives the output as the probability, and it is useful for where binary classification, where we can see if this particular case belongs to a category or not. Then now the summary is that it squashes the input between 0 to 1. It is like probabilities, where if you want to detect whether what is the probability of this being 0 or 1. Then we have hyperbolic tangent, which is 10h. Just give me a second, I'm drinking water. Thank you. So what is 10h? 10h is hyperbolic tangent, where this h stands for hyperbolic and this is tangent. 10h stands for hyperbolic tangent. It is very similar to sigmoid, but instead of outputting the values between 0 to 1, it outputs the value between -1 to 1. Okay, nice. It is helpful where it is where because it is centered around 0. Earlier the center was around 0.5. Here the center is around 0, which makes it which makes learning easier for some neural network. So it is similar to sigmoid, only the difference is it generates the output between -1 to 1 instead of 0 to 1. So imagine, let's understand it with the help of an example. Imagine we have a thermometer that can measure both cold and hot temperatures with the following scale. Negative values mean colder temperature, positive values means hot temperature. 0 means temperature is neutral, neither it is hot or cold. If it is cold, the thermometer shows a negative value. If it is hot, it is going to show a positive value. If it is neutral network, it is going to show 0. Okay, so if we want the values in zeros also, negative also, then we go ahead with this, which is 10h, hyperbolic tangent activation function. In neural network, 10h lets the value to be both positive or negative. If a neuron wants to strongly say this input is important in a positive way, it outputs a positive value. If it wants to say this value is important, this input has a negative effect, it outputs the value close to -1. This means that 10h is, so if it wants to say, the neural network wants to predict that the value is highly positive, then it is going to output it close to 1 plus 1. Otherwise, if it wants to say that it has a negative effect, then it is going to output the value close to -1. This means 10h is good for solution where being able to indicate both strong positive or negative value is useful. Okay, so this is the summary. So it makes sense now. I do understand. So ReLU, which means rectified linear unit, outputs only positive and blocks negative. Sigmoid outputs the probability in between 0 to 1, deciding whether something belongs to 1 or close is towards 1 or towards 0. 10h, which is hyperbolic tangent, is when we want to consider the negative input as well, showing that it has negative effect, and positive for positive effect. So there we use 10h. So it makes sense. Let's go and code it up. So the solution for today, how we are going to code, is going to be very similar to what we did yesterday and day before that. So I will switch to not making sense and going deep into the code today, what we have already explored yesterday and day before that. So let's start. Hopefully today we are going to make it as a short video, unlike the other videos. So let's say it is day4.py. Add it to our repository. Mention what the problem is about. The problem is about comparing the activation functions. Okay. Let's do what? Let's go to the code back again and import the libraries. First, we will import numpy as an numpy. Import tensorflow.keras dot datasets. Import mnist. We don't have to import from this mnist. From tensorflow.keras.models, import sequential. We have already explored what that is. From tensorflow keras dot layers, import what? Dense layer. Yeah, we also need to import a flatten layer because this MNIST data is going to be in the form of 28 by 28 pixels. We have to flatten it into a 1D vector, which is 784, the product of 28 by 28. Um, so for that, we will have a flatten layer. From I guess all of that is done. We have to now import pandas as PD. Not pandas. We should not do that. I guess we already know how the data looks like. You guys can go and check it from the previous videos. That we have already, what we did, we have already converted it into panda data frame to see how the data looks like. We are using the similar data set, so we are not going to do that step today. So simply we are going to import the matplot.py plot as plt. That is it. Yeah. Now we will do what? We will load the data set, and we will load the data set how x train x sorry, y validation, x validation. It should be x train y train, x validation y validation. Is that it? And we are going to load from mnist load data, and then we will, once we load it, we are going to normalize it. Why we are normalizing? Because this image, which is the shape, is going to be 28 by 28, will be in the range of 0 to 255. So we want to now put them in the range of 0 to 1. So that is why we are normalizing, and why we are doing it, because it model training becomes faster. So we will do what? X train will store the images. Bytrain will be the label. What image is, like, is it one? It represents one digit number one. It represents 7 digit. Not 7 digit. It represents digit 7. It represents digit 9. It represents digit 6. So that is what this y underscore train and y underscore value is storing. So we will do what? X train 55.0. Then we will do what? X validation divided by 255.0. Once we do that, what do we want to do? We want to train the model. For that, what we can do, we can create a model function. Def model, build model. First we will build model. We will create a function build model. So here we will pass the activation function, and whatever activation function is being passed here, we are going to build the model according to that. So what we are going to do, we are going to model, not here, model sequential. Okay, model dot add. First we will the flatten the input two-dimensional 28 by 28 images into one-dimensional 784 size image, because neural network works on 1D array. So we will do it. We will do how the input shape is going to be 28, 28, right? Then we will add the another layer. The next layer is going to be a dense layer. How many neurons we want? We want 128 neurons. I've explained already why do we want that. The activation function is going to be the activation function passed to this array. And then we have another narrow down the neuron size to 64. Now we will just output, have a output layer, output 10 neurons for 0 to 9 digits. And here we are going to have the activation function softmax, not like this. And why we are going to have softmax? Because softmax outputs in the form of probability for 10 neurons, and the sum of the probability is going to be 1. Like sum of the probability of all these 10 neurons is going to be 1, whatever it is going to output. Correct. Sorry, activation, I had a typo. Yes, activation. So done. And once done, we will simply return the model. Oh, it expects 2 lines. Once done, we are going to build the compile and train the model. So for that, what we are going to do, we are going to first, now we are going to compile and train the model on different activation functions. So what we let what should we do? We should correct this spelling. DIFFERENT, and it is going to be COMPILE. Okay. Now let's create an a list of activation functions, and we are going to have rectified linear unit. Then next one was sigmoid, and the next was 10H. We already understood how they work and how they are different from each other. Then we are going to have our history, what we a dictionary to store the history of training uh, on, on different activation. Okay. So history dictionary. And now we'll do what? We'll do what? Iterate for activation in activation functions. We have all the activations. We are going to build a model. So first we are going to call this build model and pass this activation. Once done, we are going to compile. So model dot compile. For that, we are going to have optimizer is going to be the classic add-on, and I forgot a comma. And then the loss, how are we going to measure the loss? We should measure the loss with this sparse categorical cross entropy. Why this? Because it is not, so we have 10 digits, right? So we have, so that is why we are going to have sparse, and it is a categorical output that we have to predict whether the number is 1 2 3, whether the image represented a digit 1 2 3 4 5 6 7 8 and 9. So it is a categorical representation. And then yeah, so that, then the metric for performance is going to be accuracy. Once done, how we are going to train the model. Model we are going to train how, using fit function. Here we specify the x train and y train. The validation data is going to be, let's go ahead that way. So first x train, y train, validation data is going to be x validation, y validation. Then we will have how many epochs you want, 10 epochs. How many batch size you want to. Epochs is that how many iterations the model is going to perform on entire data to keep getting better. And in each epoch it is going to take the size, sample size as 32, and you want to see whatever it is doing as in the loss, accuracy, everything of each epoch. So we pass it as verbose 1. If we pass it as 0, we will not be seeing it in the terminal actually. Yes. Once done, we need to store this training in this history variable. Here we need to pass that for which activation function are we training. Training for activation function, activation, not this activation, right? Once done, we are going to store this uh, in the dictionary called history dictionary. The history of our model, history dot history. Done. Now let's do what? Let's, we have built and trained everything. It will be efficient for us to see how the model is performing. But let's do what? Let's visualize it as well. So for visualization, I mean, how do we visualize? By seeing, looking at the graph of the loss or the accuracy of all these three, from all these three activation functions. For that we are going to visualize. So how we are going to do that? In the inside this for loop only, we are going to do what? Visualize the accuracy and loss. So first we are going to do, prepare a figure. The size is going to be 10, not 14 is to 8. We could have done that here also, right? But let's do that. It not see the map after each, for each activation function. Instead what we can do, we can see everything together. I mean, once this training is done, then we will move to the graph. So visualize it. Sorry, this should come out. Why? Because this is not dependent on the activation. This is a generic thing. Yes, so we are going to plot history dictionary. Here the activation are going, and here we are going for the loss. And here we have label as the training loss, of which activation function for that format this one. For which activation, this is for this activation. Now let's, we are going to have something similar for what? Loss for validation data. So we'll say validation. I have a typo there, validation. Uh, Oh, today we it says that today the line style is going. We can this is line style. Line style is a argument I'm exploring today. So line style is going to be dash dash, and then let's do what for each activation. Invalidation was for each activation. So here we are doing lot training and validation training and validation loss for each activation function. And once done, once it has plotted, we are going to do plot x label is going to be epochs, plot y label is going to be loss, plot title is going to be training and validation loss for each activation function. Let's capitalize it, capitalize it. Done. Now we will do what? Now we want to see the accuracy. So we'll do what? Plot training. Okay, so this is going to be different. Diff- Plot train and validation accuracy for each activation function. So what we are going to do? Plot a figure. The size is going to be 14 is to 8. Then for each activation in activation functions, we are going to plot the accuracy of this activation. And here we are saying accuracy label, not lambda. Label is going to be training, training accuracy of which activation function? Of activation. Okay, now I'm going to copy it and paste it. Now I'll go and mention it that now we want for validation accuracy, and it is going to be validation accuracy. And here also we'll say the line style is going to be dash, so that it becomes easier for us to understand amongst all those 6 lines. Differentiation for better easy differentiation, we are doing this. Now once done, we will do what? X label is going to be epochs, and then Y label is going to be accuracy, and then the title is going to be training and validation what? Accuracy for each activation function. Once done, we will simply show it. This is looking good to go. So let's do what? Compile the, not this, compile this day 4 code. And now we should be able to see the epochs training. See, initially the loss is like this. Let it generate and then we will decode it. It will, I guess, take hardly a minute. So it is done with the rectified linear unit training. We see that the loss started with 0.24 and ended with 0.01. Very good. Lost the accuracy started with 0.92 and ended with 0.99. Very good. Loss also started with 0.14. Validation loss data, for validation data, the loss started with 0.14 and ended with 0.09. Very good. And it started with 0.97 and ended with the accuracy 0.9. 5 and 7. Okay, so here we can visualize the accuracy and epochs. Did we generate accuracy? Not this one, sorry. Oh, it came on the above. So let's look at the validation losses first. We see that the oh, let me we might have to do do what? We forgot one thing, and we cannot see which line is represents what, right? So for that we need to show the use this legend function, and I'm really sorry. Come back to this and recompile. Just it is not going to take long. Trust me. Took hardly 20 seconds. So let's wait for 20 seconds, and then we will decode the training. Okay, we are almost done. So yeah, now let's understand it. We should see the training and validation accuracy for. Let's do what? Let's understand the loss first. We see the training and validation loss for rectified linear unit. First one is blue and dotted orange. Blue this. So it was decreasing, and then at this first after first epoch, it was decreasing steadily. There is steadiness, and then the orange. So for validation, it is decreasing, then increase, then decrease, then increase, then decrease, like that. So it started with that and then ended a little lower. Then for sigmoid, the training loss and the validation loss. Training is green, validation is dotted red. Okay, so the drop is huge here in the sigmoid, and then going somewhere like towards the, I mean, closing around the training is rectified linear unit only, but it is a little higher. So there is huge, there's this unsteadiness, right? And then for validation data, it is red dotted. So this is it in decreasing, 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 decreasing. So this is better. For the sigmoid is the for validation sigmoid is steadily decreasing. For training, for the 10H, the training loss and validation loss, tangible. What was the name for? Let me go back and understand. It was just a second, second. Ah, hyperbolic tangent. For hyperbolic tangent, it is violet and then the dotted dark violet. So violet dotted. So this one. So it started, the drop is not that much, but it is going some. It is like going like the rectified linear unit, and the validation is also decreasing only. But yeah, so for me, I think the tangent is better for the loss, but I need to, you know what, see that what ChatGPT has to say. So I'll close it. I'll open this now. Accuracy. Now see the accuracy. Accuracy should be, become stagnant after some time, and it should increase. For rectified and linear unit, the accuracy is blue and dotted orange. Blue is like it sharp. There's sharp increase and then slowly increasing, and then orange increase, decrease, increase, decrease. So there is unsteadiness, like we saw in the loss for rectified linear unit. For sigmoid, green and red. Green, there is again sharp, like we saw in the loss case, and then slowly increasing. Red, there is slowly increase, right? But not that increase, decrease, increase, decrease we saw in the rectified linear unit. Then let's look at the training and validation accuracy of hyperbolic tangent. Hyperbolic tangent, it is violet and the dark violet, so it is this, not this, this and this. Yeah, so it is there. It is not a sharp turn like what uh, the loss we saw for hyperbolic tangent, and this is how it is looking. It slowly increase, then a slight decrease, but the steadiness is there. So again, for me, I think 10H is better, but let's say I've taken screenshot in case I have to supply it back to the chat GPT to understand. But chat GPT has, you know what, provided a little bit of the result. So let's say expected observation. What to look in the results? Lower loss is better. Look for the speed at which the loss decreases. Faster convergence indicates that the model is running well. Okay, validation loss should be similar to training. If the validation loss is much higher, it suggests okay. Higher accuracy is better. Check how quickly the model reaches the higher accuracy, whether it generalizes well to the test. Okay. So they are old function. They tend to be slower because they can saturate meaning gradient very well, and meaning is very small, and learning stops progression effectively. So it says that the ReLU rectified linear unit is mostly better because it converges fast, avoids vanishing gradient problem, and generalizes well in the most cases. Okay, we saw that it is learning slowly. We saw in the graph that there is steadiness, and that sigmoid can sometimes overfit due to the saturation, leading to poor performance. Okay. Again, same thing here, 10H. So that is why it is saying rectified linear unit, because there is sharp increase. And what to look in the result? Lower less loss is better. It should achieve higher accuracy quickly. So if I go back to the desktop and open this and then open this accuracy, which one is achieving the accuracy faster? So almost similar, but it is achieving the accuracy faster. This is the highest accuracy it reached. That is why it reached the highest accuracy first. This rectified linear unit, and the loss, minimum loss is what we want. The for training the loss, there is it loss is like minimum. It started minimum and then gone minimum. So that is why it is saying to go with the rectified linear unit. Okay. Okay, so we are almost done with today's problem. Let's commit the code. Day 4, commit minus add code for day 4 and push it to our main branch. And let's go and see how it looks. We can see the code here. So yeah, so we let's to conclude, we have learned a lot. We learned that three different type of sigmoid, sorry, activation functions, how they function, what I mean, and what is the difference between them, and we also saw it working and the difference through with the help of an example. So thank you very much. You will soon see the textual format and the video on the YouTube channel and the textual post on this tech journal, and we will come back tomorrow and solve the day 5 problem. Thank you very much.